so here is our plan, and so originally I planned to go through the proof of the convergence of CG, but I look at my old lecture notes. I thought it was too much. Maybe it takes kind of long. It has a long preparation because we have to introduce this Krylov subspace thing, and we have to prove a few polynomial theorem. So instead of that, I'll just post my lecture notes on Canvas. So if you're interested, you can take a look at it. So I also put a few references. So I think our official textbook, they don't have this, let's say, a full rigorous Krylov subspace method proof. So I learned this back when I learned the solvers, linear solvers for linear system. Okay, so there are lots of Krylov subspace packages. I mean, it used to be pretty much in the national lab. So for example, each national lab have their numerical linear algebra package. For example, Cambria has Trilinos, Lawrence Livermore has Hyper, so and etc. But yeah, but anyway, so let's go through our AutoGrad notebook, and then we'll have our coding homework 2 posted. So so the midterm will based on our current. So originally I wrote my midterm based on the proof of Krylov's proof CG, and so then we'll have one problem less. So I'll post coding homework and a practice midterm. So then you guys will try it. Okay. So on Thursday we'll do something new, but next Tuesday we'll do a review. Okay. And then next Thursday we'll have midterm in class. Okay. Good. Any questions? Cool.
No, next Thursday.
Is it visible?
Yes.
So so today we'll introduce Python's AutoGrad function, and we will so we'll learn how to use a very simple, very handy tool in Python. It's called TQDM. It's a progress bar. So I like it a lot. So let's first import everything. So this is Tosh. So math is, we just need a few constant, for example, pi. Okay. So this is time, because sometimes it's too fast. We need, later on we'll see, we need a little thing from time. And time is a very handy package as well. So for example, it can record how much time has passed for our program. So it's the MATLAB counterpart is TikTok. So if you have used TikTok to profile your code, how fast does it run? So normally, for example, when we do research and when we try to compare our code with, so let's say we're trying to compare how fast our program runs against previous state of the art. We normally have to compare the CPU time or the GPU time. Okay, so that's fine. Thank you very much. Okay. So then again, back to the sample problem. Okay, so we do a linear regression. under the setting of polynomial fitting. Okay, so what happens is on the interval from minus pi to pi, we want to use a cubic polynomial to approximate this function, which is sine of x. Okay. So sine of x looks like so on minus pi to pi, sine of x looks like this. All right. So which is, so if we have a cubic polynomial, so I mean, if minus infinity, so this is some cubic polynomial that using our eyeball to gauge its approximation capability, so at least from minus pi to pi, our cubic polynomial can approximate this, but it requires rigorous proof. But here I just want to tell you guys that cubic polynomial can approximate at least one period sine function on the fixed interval. Okay, so, and what we do here is we minimize. So this P3 is the polynomial space of degree 3. Okay. So this little p is in this big P. So what this means is, for this function f, we find a cubic polynomial such that the distance between these two are minimized. So this is a perfectly minimization problem, and this is approximated at this. Okay. So this is our cubic polynomial. Okay. And we create a discrete set of points. So this d sub h is, so we have interval from minus pi to pi, right? But apparently, I mean, it's impossible for a computer program to compute exactly the integration on this interval. For example, sine of x. It's possible for polynomials because we can evaluate it exactly. But for computer program, it doesn't know, right? It doesn't know. Okay. So the way, even though we haven't done numerical analysis, but so the idea is we do sampling. Okay. All right. So we create a linear space, which we'll down below, so that these are the sample points. All right. Then we can approximate this integral. So, so let's write down this integral here. So the L2 norm of a function from minus pi to pi, okay, is computed by, we take this function square when we compute the integral, but so this one is approximated by what we call the Riemann sum. Okay. So we can use more accurate what is called the quadrature. A quadrature is much more complicated, so to avoid confusion, so we won't go through detail in that, but this is a very nice research area. So if you're interested in using neural network to compute highly precise integral, written in our PyTorch code, and you already know PyTorch, then you can contact me. I have a very nice little project for you to try. So the Riemann sum, we just use definition. it's just we sum up all the small intervals, okay, such that we evaluate this function at these points, okay? And delta x is, let me open up the light for a moment. So delta x is xi plus 1 subtract xi, okay? All right? So then what happens is, this is our loss function. So this is called the loss function. That is the difference between our polynomial and our target functions. And it's approximated by this sum. So now we recall what we had on each line. So first let's set the D type. So normally D type basically is the type of our variables or tensor. So we can have other types. So Torch has lots of types. The most commonly used type, there are three. Okay, so integers, float, and double. Okay, so this is typical three types. So in scientific computing, so there are lots of, so for example, if we want to store indices, we want to track iterations, we use integers, because if we have learned Fortran or C, we know that in Fortran or C, we have to specify the type explicitly. So, and in MATLAB, the default is double, which means we use 64-bit to represent the number. And the float is we use 32 bits to store a number. Okay. So it's we use 24 bits to store the significant digits. So this will be taught in a typical numerical analysis class. I just want to let you guys aware that float is relatively like lower precision than double. And in training neural network, normally float is used. And even sometimes it's used half precision, which uses 16-bit. But 32-bit is 24-bit is used to store the significant digit. 1 bit is to store the sign, and the other is to store like the exponents, because we want to express a function using this exponential. And then we create a linear space. So let's add a code up above to explain the linear space. So the linear space is basically so the syntax is linear space is it's like we said here. The first one is start, the second is number, the third is step. So for example, if we print 0 and 5, we're gonna get 5 points evenly spaced from 0 to 1. Okay. But this will not give us the ideal 5 intervals. It will give us 4 intervals. We'll see each one of them has like 0.25. So we'll see. You see that? So if we want to create 5 intervals, we have to add 1. Okay. So that we have this. If we want to have, for example, 10 intervals, so from 0, 0.1, 0.2, we're going to have add 1, so that because it's like this number, this step is inclusive in how many points we have. Okay. So for example, if we want to have 10 intervals, we have to have 11 points. All right. So then the step, this delta x, is then x1 subtract x0. So basically this is like pi subtract minus pi divided by 2000. Okay. So this should be same 2000 minus 1, sorry. So this should be the same as start, which is minus pi, sorry, and subtract subtract start, which is pi subtract minus pi, then divided by number of intervals, which is 2000 minus 1. So you can check these two are the same. And then this y is the function value. Okay? The function values at the sample counts. So this is our target. And then we just initialize. Okay, so we initialize A, B, C, D, and we compute our prediction using the current parameters. So we call, in the context of a neural network, A, B, C, D are called parameters. Okay, and it's a parametrized model. So we compute our prediction using the current A, B, C, D. So the values of A, B, C, D in implementing a gradient descent, it will be overwritten in every iteration. So as we can see, we didn't specify like number of iterations here. So let me explain this with later. So with is a very nice decorator like Python thing. We can just read here. Okay. So just for this iteration, so number of iteration we set 2000, and we compute the forward pass, and then we compute the loss function. So for example, so the order of our operation is predicated by the parentheses. For example, we first compute this, and then we compute this, and then we compute this, and lastly we'll multiply delta x. Okay. So for example, so what happens is let's give an example. So for example, if we have, let's use U. So if U is torch, let's use a range. So let's just use 5. So it's from 0 to 4, okay? Right? So now what happens is, if we do U this, okay? So it's the same thing as U. So this double asterisk just means exponential. So U raised to the power of 2. So U dot power of 2, so and U raised to the power of 2, so they are the same. And it's computing element-wise like square or power. So for example, if U is 0, let's use D type equals. This is blocking my view. Okay, there we go. All right. So and then this is compute that. So now what happens is if we do first we raise to the power of 2, and then we do sum. Okay. We just sum it up. So for example, we sum these 5 numbers up, we get 30. So, and this is how we compute the loss function. So y is our function value. So y is here, is our function value at the sample points. Okay. This is our prediction at the sample points. So for example, and then we take the square. Okay. And then we take the sum. It's exactly the formula we have here. All right, in this sum, and then we multiply the sum by this delta x, which is we approximate the Riemann sum, so we multiply with the interval size, and then now we compute. So we compute So in the world of neural networks, I mean, why neural networks become the pilot of, let's say, modern AI and things, because like 20 years ago when I went to grad school, we're still learning, for example, for example, in facial recognition, we're still learning Fourier analysis, so it's not like this. So one of the pilot of this neural network becomes like a paradigm, let's say, in deep learning is because of backpropagation. So backpropagation is nothing but chain rule. Okay. So for example, so it says the following. So for example, if our prediction is denoted by h of x and it has parameter w, okay, subtract f of x. So we sum x up. So this dh is the collection of points, the sample points we had. Okay. So let's ignore delta x for a moment. Okay. So this is actually our loss function. Our loss function is a function not about x. It's actually our loss function is about the parameters. So it's about the parameters. So our loss function is a function of parameters. So our parameter is a, b, c, d in this case. And what we want to do is we want to take the derivative. So we want to compute. We want to compute this. So we use nothing but chain rule. So if we use chain rule, what we have is still the sum. So we take chain rule. So this is the outer function. So the outer function is h evaluated at x point with the weight, or say parameter w, subtract f of x, the multiply, so by chain rule, this is partial h partial w, okay? So this is chain rule. So the computer science people give it a very fancy name, backpropagation. But it's nothing but chain rule, like we learned back in calculus 1. Okay. So this is nothing but chain rule. And okay, so now let's look at chain rule. So then this one, so we have a 2 here. Sorry. So the first term is our outer. The chain rule derivative of outer function. Okay, so the y underscore pred, our prediction is this h function here. And okay, and then the grad a. Okay, so which is the gradient with respect to a. And then we need to explicitly evaluate this. Okay. So W is like a vector of A, B, C, D. Then it's straightforward to see that. So if we have if we want to take gradient of A, it's just, so we take gradient of H with respect to A, we get 1. Therefore, we don't change the outer function. And if we take gradient with respect to B, we get X. So then we want to multiply X there. And similarly, we want to multiply X squared and X cubed. Okay. And finally, we take the sum. So and then this is we update the parameters A, B, C, D using the gradient descent. So let's add one more line here. So it's called in-place operation. So Python has that in-place operation, which is very like Fortran in-place operation. That is, an object will be replaced by a newer one instead of allocating a new memory. I mean, this variable is being replaced. Like it had the past trace is being totally erased from the memory. So it's some memory efficient operation. So let's give an example. So if we have v equals, for example, torch a range, okay, 10. All right. So this is from 0 to 9, right? I mean, let's print v. Okay. So now what we want to do is we have this operating. For example, if it's plus equal, if it's plus equal to, this is an in-place operation of saying we left v equals v plus 2. So what happens is we add every element of v by 2. So let's print v again. Let's see. All right. So as we can see, every element of v gets printed by 2. Sorry, gets added by 2. So we can do this. Okay. So for example, divided equal 2. I mean, use this with caution. Okay, so especially when we have an unspecified type in Python. So divided equal should be used with caution. So this is in-place version of saying we let v equals v divided by 2. So let's print v again. B type. Okay, so let's read the error message. Yeah, let's read the error message. Okay, so it says result type. Yeah, that's why I say use with caution. So result type float can be cast to the desired type long. So we have a runtime error, and how to fix it? We can. I mean, so here I want to teach you guys how to fix the bug. So if you want to fix a bug, you can exactly search Stack Overflow. Okay, so a simple way is just to search Google. So the thing we need to do is we specify the B type here, right? Or we do something like this. Okay, this is just converting this, which has integer. So we can see when we print, it's an integer. So long just means long here type. Long is we use 64-bit to represent an integer. It's basically a double precision integer. So let's search it. Let's search the runtime error. Okay. So if we search it, so you see that. Oh, very nice. So we have this bin here. Oh, cool. Yeah. Okay. Here we go. This is wrong though. But okay, you can use type. Yeah, this is good. But permute or unsqueeze, this is bad. So for example, you can use type, parentheses, or dtype method to check the data type of your tensors. So, I mean, if we encounter error, we can simply Google. So, I mean, 100 out of 101 times, it's already answered on GitHub or on Stack Overflow. Okay. So, if we do this, okay, so we'll see. So for example, so now we convert this to float and we print the v, we get this from 0 to 9, and v plus equal 2. So then this becomes every entry gets plus 2, and then divide equal 2 is we basically divide each entry by 2. Okay. So now let's look at here. These 4 lines of code is basically saying our parameter equals, so in place version, so in place operation such that we let parameter equals parameter subtract learning rate, okay, which is short for LR, times gradient of these parameters, okay? So which basically that. So let's run the code. So here we have, okay, so here we have P bar just means progress bar. So how to use this is, so let's give another example, so which is about TQDM. Okay. So for example, for I in range 10, so this is a common way of tracking our gradient descent is we print the error at each iteration. So for example, if we print, for example, I'll touch exponential, oops, minus I. Oh, must be tensor, okay. So let's try math. Okay. So basically what happens is we basically print a number at each iteration. Okay. This is not so nice. I mean, why it's not so nice? Let's just do pass. So we don't do anything. If we add a TQDM here, it adds a little progress bar. And what we can do here is, so for example, it not only tells us how many iterations left. Okay, it's too fast. Maybe let's try this. Oh, it's still too fast. Okay. So let's try use our time. So okay. So at every iteration, the program just hands out for 0.02 second, and let's try this. It will show something very nice. So it's a progress bar. So it keeps track of things, and it's very nice. So, and then let's look at the width syntax. Okay. So width, we can use what we had as a template. For example, this width TQDM, and the syntax is total equals. So what happens is, so I'll explain. So width is something very nice. The Python syntax. There are lots of useful. For example, if we do 1,000, okay, as p bar, all right. So then with this width, okay, keyword, the p bar is being initialized as an object. So then we can do whatever we like with this p bar. So for example, we can do I in range 1,000. So we still do this. Okay. And so when we let TQDM be outside, so this is applying TQDM as a function. TQDM is a function and also an object. So when we use TQDM as a function, it's kind of wraps this range like a wrapper, and produces our progress bar. But this way, the progress bar is being initialized separately as an object. Therefore, we need to update progress bar after every iteration. So, okay. So we'll see something very similar. However, we can do even something more interesting is we don't have to update our progress bar after each iteration. So for example, if we can update it every 100 iterations, so for example, if I modulo 100 is 0, we update it like 100. Then we'll see our progress bar will be updated every 100 iterations. Okay? Yeah, we can see it more clearly if we set this figure. Maybe 6. Okay? I mean, it's a handy way of tracking progress interactively. Okay? So now it's back here. Okay? So now we have every component of our code of set description. Okay? So for example, the set description is because this p bar has this progress bar, right? We can set a description besides this progress bar. So you'll see, for example, we can set p bar, set description, and we'll put a string here. So for example, so I'll explain the syntax here, and then later, and we set description. For example, we can set, this is, the description is ith iteration. Okay, so let's try this, see what happens. All right. So as we can see, we have a little description update here. So what does it mean by this f is a nice f string introduced in Python 3. So this is f string. So for example, we can have, we can let pi equals math pi, and then we print a string, right? So for example, we can print the string pi is approximately 3.14, right? Then it prints this string, right? But if we have a number, so print pi is approximately, we can use a curly brace. So if you are in VS Code, it has a different color when we put a curly brace here, but you see it's, when we add this f in front of the string, it changes color, you see? So it changes color here. So now, here, the parenthesis becomes a variable wrapper, so we can put a variable here. So for example, we can put pi here. All right. But this digits is too long. So what we can do is we only want to print, for example, the first, let's say, 5 digits. What we can do is we can do column. So this is 0. We don't have to put 0 here. And 5. This means we print this as a float, and then only 5 digits. 5 significant digits. So we can put 2 here. Okay, but it doesn't affect, right? But when we put, then this will affect, which is, oh, okay, still doesn't affect. Let's try. Okay, so yeah, the first one. Okay, let me think of a scenario that this does matter. Yeah. All right, let's just keep this way. So the idea is this one is the significant digits before the radix. This one is after the radix. Okay. So if it's all 0, it seems doesn't matter. Okay. Anyway, so now we have everything. So for example.
Excuse me, I have a question about this. You use like the for loop for the variable t, but I don't see any t like in the code.
That's right. You can change this to nothing.
So how is it going to operate? I mean, like, what's going to be like in the iteration?
Okay, so let's try a for loop. So for example, so we don't have to because like I said earlier, for memory save purposes, we can overwrite A, B, and C, D in each iteration. So we don't have to track the iteration number. So for example, in range 5, okay. So what we can do is, for example, so this is a typical Python. So for example, we let let's not use, let's Z equals an empty list. So we can do Z append, or Z, let's do Z equals 0. Okay. Sorry. For example, we can do this. We'll see that if we don't have to track the loop, we can do this. So every iteration we plus 1 to Z. So the other more nice thing about Python is we can use something called list apprehension. So for example, if we want to do, so we can do something like this. So 1 for nothing. Okay, so if we have an underscore, it means it stands for none. Okay, so the underscore means none. If we print Z, we'll see Z has 5 ones. Okay. So I mean this list comprehension doesn't restrict to, I mean, numbers. For example, we can print hello, then this is 5 hellos. Okay, so we can change this to I, it doesn't affect. You know. So here is, basically is we run this many iterations to answer the question. Okay, so now we're ready. So this is a full implementation of, we'll see that the loss function, so at every iteration, the loss function is printed with 6 digits of accuracy. So finally, we have this approximation. So I forgot to attach this plot figure, but let's try to plot it. So, as long as PLT. So, so let's PLT. Let's do PLT subplots. So what happens is we're gonna plot. So for example, x, y, is that x1? So we're gonna set label. So the label is our target function. Okay, so this is our sign function, and then we plot another one. PLT plot. The second one will be our prediction. So by the way, if you guys are using Visual Studio Code, you can get a free version of, using your EDU email, you can get a free version of Copilot, which is very handy. So I rarely type my code right now. You know, so, but anyway, so then we do PFT show. So for example, the Copilot will auto-complete the code for me. And then we have, so we need to add a legend. Anyway. Okay, so this is our target function, and this is our prediction. So as we can see, you know, this is a result of we using a cubic function to approximate sign function. Okay, so now let's go through this. How to compute gradient in PyTorch is autograph. Okay. This part is way too specified to be generalized to big scale problem. Okay. So instead of doing this, So what we can do is we can use PyTorch's autograd to take gradient of a variable. So without computing the function, or let's say the gradient by hand. Okay. So the keyword is when we initialize a tensor, we put this require grad equals true. Okay. Okay. So if we print A, it has this. So this is like requires grad as true. But now it has an extra attribute called A dot, so grad. Okay, so right now it's none because we don't know what the rate of change of this A with respect to 2. So let's see another. So if we don't require a grad, so let's see if we have C, if we just have torch tensor, let's say 5. Okay, we don't put this require grad, and now let's try to print C grad. So Python will give me, I'm not sure, originally it's error, but I'm not sure if right now it's back compatible already. Oh, it's nice. So, but it's still none. Okay. Yeah, good. So now it's made back compatible. So we fix this error. So this is fixed in PyTorch 2.0. So originally this will give me an error if we don't put require grad here. All right. So now what happens is if we compute this, all right. I mean, this is just a 3a cubed subtract b squared element-wise. So each component of f is computed by this. Okay, so we have something very interesting here. So not only computes this, so this tells us, I mean, this print tells us, okay, so we are tracking the gradient of these two functions. Okay. I mean, this is taking partial derivatives. So if we do that, so this f dot backward is the procedure of taking gradient. Okay. So if we do that, so we'll see that we have the A gradient is indeed like the gradient computed by hand, and B gradient is the gradient computed by hand. So the other way of checking, so there is a more relaxed method than equal equal. So equal just means if they are equal up to the machine precision, then this is true. If they're not, it print false. So there's a more relaxed version for flow number. It's called torch or close. Okay. So for example, we can do this. So this will give us true. You know. So it means this tensor is equal to this tensor. Okay. And now we back set A and B grad to none. Okay. So the reason to do this is every time we perform computation, after we perform a gradient operation, we want to set this to none, otherwise it accumulates and will give us error when we do it twice. So we'll see in a moment. Okay. And now we can take sum, okay, of this. And let's do G backward. Okay, so we'll get the same number. So 36, 81, and minus 12 and minus 8. Okay. So if you're interested in external grad, this just means, so I add a comment here. So first component and second component modifier, because f has two components. Okay, so if we add a 2 here, yeah, let's set A grad and B grad to none. Okay, so if we have this external modifier, if we add a 2 here, we'll find the second component of f. Okay, or so try to backward through a graph second time. Fine. Okay. Let's do that. So now it's good. Yeah, so that error is very common when we play with it. But let's just don't talk into detail about that. It's involves something in computational graph. Okay, so if we have this and we check A grad again, we'll see the second component with respect to the second component got doubled. Okay, right here. So this is what this modifier is doing. Let's change it back to like this. I think the vibration will go through with the wall. Oh, it's much better. Thank you very much. Thank you. Okay. Oh, that's interesting. So I didn't clear the A grad. You see? So here, what I did, so here is a typical example. When we don't clear the gradient after taking derivative operation, okay? We didn't do this when I tried to, rerun this. And then we find the gradient got accumulated. Originally it's 162, okay? It's getting accumulated at 81. So this will actually cause trouble in our gradient descent algorithm. So if we want to do this, we want to set every time this to none, okay? After every iteration. So we do that. We do this, and we'll see it's back to this 24 and 81 again. 36, sorry, and 81. So otherwise it's getting accumulated, and it will give us much trouble. Okay. So now let's try. So now we implement gradient descent using autograph. So everything is the same, except we have this required grad equals true. So let me try to make this look nicer. Yeah, why? I'm not sure if Colab had this TEP 8 format, but okay. So at every variable we have this grad equals true. Okay. So same thing. Everything is the same. Everything is the same. Now we set the loss function, but instead of manually compute the gradient, we call the auto differentiation chain rule or back propagation by this little function. Okay. So we do loss backward, and here. So this is width, we use width. So if we want to use auto gradient, auto grad manually like this, so we call a grad function, then what happens is we have to wrap this in the width wrapper, okay? So then we set, so this is like setting A grad to 0. Okay, so this dash means in place operation. So 0 dash means in place version of 0. Okay. So this is with 0 the gradient. So this is the same as we set B grad to 0. Okay. So now we try this. Okay. All right. So we get the same result, hopefully. So 0, 0. So because it's as we can see here, because sine is an odd function, the even coefficient are all 0. So this should be same as above. Okay. Yeah, same numbers as here. Okay. All right. So last is we want to implement linear regression using this matrix multiplication algorithm. So our linear regression algorithm will always be actually in this form. That is, we minimize the weights or parameters. So X is called the data matrix times the weight subtract 1 square. So this is our linear regression or least square problem we solved in our homework a couple times. Okay. So for functional approximation, this X matrix is as follows. Okay. So this W is ABC. Okay. So this dimension is number of samples. Okay. This dimension is the number of features. All right. So the number of sample is nothing but our sample points. For example, in our case, we have 2,000 sample points. So in our case, this equals 2,000 sample points. So the number of features is actually the value of a constant. So this is very common in linear regression. Using linear regression to approximate some function. So this is 1, and this is x1, this is x1 square, and this is x1 cube. Okay. So as we can see, if we do matrix multiplication, the first row will be, okay, a plus bx1 plus cx1 square plus dx1 cube. Okay, and we do the same. So this is 1x2 x2 square x2 cube, etc. Okay. So then the ith entry of this matrix. So by the way, this is a, for example, this is a 4 by 1 matrix. This is a 2,000 by 4 matrix. Then overall, this will give us a 2,000 by 1. Okay. So this is our Y prediction. And the ith entry. So the ith entry of the tensor is our prediction at xi, at the ith sample points. And then we want at the ith sample points okay, as close as possible to our true functionality. So, okay. So what we can do here is so right here, when we initialize the weights, when we do this when we do this empty parentheses, then A is being initialized as a number, as a scalar. Okay? So we just copy this part. So now we want to implement this. Okay? We just copy everything and paste in the cell here. So we want to modify this implementation using the matrix vector multiplication. So what we want to do is we just leave one vector here. We change this to W, and we do 4, 1. Okay. So what happens is, all right, and what we have to do is we want to multiply W with this data matrix. Well, how to build the data matrix? Okay. So X is our linear space, which is, so if we print X shape, it will be 2000 and nothing, or torch size 2000. Okay. So what we want to do is we want to build a matrix so that it has 4 columns, and each column is like is related to X. Okay. So for example, and this 1 can be simply implemented as X raised to the 0th power. So how we want to do this is we simply do our capital X. So capital X is our data matrix. Is torch. So here what we can use is we use something called stack. So how do we stack? We stack X raised to the 0th power. So this is a column of 1s. This is a column of X. Yeah, we don't have to input this, but I just want to illustrate the data matrix. And we put a column of 2s, and we put a column of cubes. Okay? And we stack this in the last dimension, which means, so we have the first dimension, or 0th dimension. Dimension 0 is 2000, and then we stack these 4 in the second dimension. And in the second dimension, we should put dim equals -1 here. So if we do this, okay, and now we print X shape, we'll see it becomes our 2000 by 4 matrix we want here. Okay. So then we can use matrix multiplication to multiply these two together. So instead of this, all right? Yeah, so instead of this, we can simply do, so X matrix multiplication of W. All right? And then we do the same thing. And here, instead of 4 line, we have 1 line. So instead of a 4 line, we have 1 line. And we'll see if it, went through. Okay. So let's try it. So, oops. It becomes an A. Okay. So.
I think it's the last print statement because you have A.
Yeah, let me fix this. I think it's caused by some accumulation problem. Okay, so it's okay here, but too far. I think let me make, so I think it's about the initial guess. So let's try to put 0.0 1 here. Okay. Wow. So this is working. What goes wrong? Oh, yeah, sorry, I forgot to put, so after the matrix multiplication, we have to multiply with delta x, right? So otherwise it's stupid. Okay, there we go. Yeah, but it's too slow. Power 2. Wait, no. Already multiplied by x. Okay, so this is where we're at. Yeah, let me fix this after class, and I'll update the canvas. Okay. But our goal is to implement CG using this, which will be a step-by-step instruction in the homework. Okay.
Thank you.
So I have a question. So, in the midterm is going to be the next Thursday, right?
Yes.
So you're going to in the canvas you're going to upload a sample.
Yes.
Okay.
Yes, I will.
So up to which lecture
Say again.
up to which lecture we need to study for the midterm?
So for the midterm, today's lecture is the last lecture.
Today lecture is the last. Okay.
I have a question. Will you have all of our homework graded before the midterm? Will you have all of our homework graded before the midterm? Homework, like all of our homework that we've turned in? Or like, well, I mean, I
Yeah,
guess
sure.
2 and then 3. That'll be graded.
Yeah, also, the solution will be posted.
Okay, cool. Thank you.